Okay, class, good afternoon, and welcome to another session of Physics with Trig. I hope that you all have had a good week. This will be our last session for this week, and I wanted to introduce Chapter 6. And I have sent to you the notes. You should have your lecture notes. You should have your equation quiz, and you should have your first homework set for this chapter. So, hope you all are ready to get started. I'm not at home, and I was out and about, so I haven't had a chance to check if you all have submitted the take-home exam for the midterm. So please send that in. It will not be considered late if I can get it, say, around 3:30. So after I end the session, I'll give you a few more minutes to get that done and submit that to me. So I'll give you to 3:30, maybe even 4 o'clock. So I'm not at home, so I won't have time to check it for another couple of hours. Okay, do I have any questions from anyone concerning anything? You can come off mute and ask your questions, or you can go in chat if you have any concerns. Okay, so we'll go ahead and get started on our new chapter. Okay, so we're in chapter 6, and chapter 6 is entitled Work and Energy. So when you think of work, you think of actually doing labor, some job, or completing some task. And we know that when you do a good workout, you expend a lot of energy. So this chapter is going to pull together most of what we've learned from chapters 1 through 4 in particular, and a little bit of chapter 5, as we explore the physical understanding of work and energy. So we're going to begin with the definition of work. So you notice here in the picture to the left, he's pushing the car. And we know that any push is a type of force. And then this line here that's labeled with S, that is the distance that he moves the car. So we're going to define work. We use an uppercase W equal to force times distance. Now you notice here that even though force is a vector, you can tell by the arrow, and S, which now is my displacement, is a vector. Here we're only talking about the magnitude of the force because this is not a vector. Now, we know that force is measured in newtons, and distance or displacement is measured in meters. So now we have a new unit called a Newton meter, and we give it a new name, and that new name is the joule. So we have a new unit. So I'm going to take you now to the equation quiz to show you how we're going to be completing another equation quiz. So I hope that you all received this new equation quiz. It's abbreviated, but I did put some of the information that you had from previous ones on this one. And this one has highlighted the new content. Of course, when you print it, you can take away the highlights. So here you see I have derived units. So the derived units, we've already derived two already. The kilogram meter per second square, of course, that is our Newton. So we've already derived the Newton. A slug foot per second square, that's a pound. We've already derived that. And now we have another unit called the Newton meter. The Newton meter, we give it a new name, and we use the symbol uppercase J, and that stands for joule. So the unit for work is the joule. Okay, so now this is an example, a simple example of force through a distance. So he's doing work. So we have other units for work. The SI unit, we say, is the Newton meter, which we call the joule. Another unit in the SI, not the base unit, not the SI unit, but another unit that's I would say the metric system, is the dyne times the centimeter, and we call that an erg. And then in the English system, we have the foot pound, but you see the force comes first, so it's pound times foot, but we don't call it the pound foot, we call it the foot pound. So we kind of reverse those two terms, but that is the English unit for work, the foot pound. Now we have an example of work where the force is applied at an angle, like pulling a suitcase. So you know when you pull a suitcase on wheels, even though you apply force, you're pulling at an angle, the suitcase actually moves along the horizontal. So in this case, we have to see what is the component of the force that's acting along the horizontal. And of course, we know that that is F cosine theta. So to determine the work here, we can't just say F times S because F is applied at an angle. So we say, what is the component of F that's actually doing the work? And that's F cosine theta. So here we have over here this chart to help us to know what is the cosine of various angles. And we know that the cosine of 0 is 1. That's why in the first frame here, we did not have to put the value cosine of theta because cosine of theta is cosine of 0, which is 1. So therefore that was eliminated. But here, when it's at an angle, we have to include the fact that the angle makes a difference in the equation. So this is actually the first equation where cosine of 0 is 1. Now, we also have sometimes where the force is applied perpendicular to the motion, and therefore it's at a 90-degree angle. And of course, it's going to always give us no work because cosine of 90 is always 0. Or we can even have negative work because cosine of 180, we'll see, is negative 1. Please feel free to either go and chat or you can stop me if you have any questions. Okay, so here's an example. Find the work done if the force is 450 newtons, the angle is 50 degrees, and its placement is 75 meters. So my equation is F cosine of theta times S. F is given 45 newtons. Cosine of theta is given as 50 degrees. And S, my distance that it moves, is given 75 meters. So of course, that's a very easy problem to solve. So therefore, you want to know this equation. So let's go to back to our equation sheet. Okay, so here we have our new equations. So number 35 is where you're going to write your first equation. So my equation says that work, uppercase W, equals F cosine of theta, okay, times S. And of course, the unit is the joule. Now, of course, when theta equals 0 and cosine of 0 is 1, we just have F times S. But this is the proper way to write that equation. You notice here that we're using uppercase W. So uppercase W will always stand for work. Earlier here, we used lowercase w. Lowercase w will always stand for weight. Okay, so weight is in newtons, work is in joules. Okay, that's our first equation in this chapter. Okay, work done by a constant force. Now, I wanted to make sure that you understood that the force remains constant. In other words, we don't have a variable force, although later on in the chapter we are going to introduce a variable force. So earlier I introduced to you, or I said to you, that there can be negative work. And what is meant by negative work? Well, in this first frame, you see he is applying a force upward. And he's also moving this weight upward. So that means then that the force and the displacement is in the same direction, and therefore we have positive work being done. But here, you see, even though the force that he's applying is upward, he's actually lowering the weights. So that means then that my force that is applied and the displacement that is moving is 180 degrees. And we saw earlier that the cosine of 180 is -1. And therefore, this is an example of negative work. So negative work occurs when the force is applied in a direction that's 180 degrees opposite of the displacement. Okay? Now, work done by a constant force, an example of accelerating a crate. The truck is accelerating at a rate of 1.5 meters per second squared. The mass of the crate is 120 kilograms, and it does not slip. The magnitude of the displacement is 65 meters. What is the total work done on the crate by all of the forces acting on it? So remember our free body diagram, because remember, we learned in chapter 4 that we can have all kinds of forces. We can have the normal force, we can have weight, which is a type of force, frictional forces. Okay, so that means that before I can find what is the work done, I must first identify all of my forces. This is so important in this chapter. So you notice here that because the equation says that work is force cosine of theta times the distance. In these problems, we must first identify the forces. So this problem is just a good example of how we're going to first, in order to find the total work done, we've got to identify all these forces. So we have, in this picture, we have frictional force, and it's static because it says that the crate does not slip. And of course, we have the normal force and we have the weight. So let's solve for the work. All right. The angle between the displacement and the normal force is 90 degrees. So this force and the displacement is going to move along the x-axis is 90 degrees. And we already know the cosine of 90 is 0. So no work done by the normal force. Okay. Now, how about the weight? The angle between the displacement and the weight is also a 90-degree angle. So therefore, no work done by the weight. What about the frictional force? What's the work done by the frictional force? So here we see that the angle between the displacement and the friction force is 0. And we now know the cosine of 0 is 1. So what is the equation? Newton's second law says F equals ma. So my static frictional force, F sub s, is equal to ma. So we have mass times acceleration. That gives me my frictional force. Then to find my work, I say my work is equal to the force times the cosine of the angle between them. In other words, in this case, what is the angle between this force and what is the angle between this force and this displacement? Now, we have the angle between them, of course, is 0 because the object is moved, the force is acting this way and the object is moving this way. So I have cosine of 0. So I have multiply all of this out. This, of course, is 1, and I get my work. And my work, of course, is a Newton meter, which is a joule. So now I have the work done by this force. Only one of them contributed to the work. Now, we have what's called the work energy theorem. We're going to understand now what is meant by the work energy theorem. So it says, consider a constant net external force acting on an object. The object is displaced a distance s in the same direction as the force. But we know from Newton's second law here that the net force is equal to ma. So here I'm simply replacing the net force with its equivalency, which is mass times acceleration. So that's my first equation. And my next equation, we're going to replace the term AS, which we have a familiar term from our kinematic equations called AX. So if I solve for AX here, I get 1/2 V final squared minus V initial squared. So you see why it's so important to know your kinematic equations. I cannot stress to you enough how those first 3 chapters form the basis for everything else you're going to learn in this course. So make sure you recognize this as one of the kinematic equations. And here I solved for AX. And X is just my displacement. So in this chapter, we're calling X S, because when you think about X, you think about displacement, and this S, since it's going to be a scalar, it's really just the distance. So when I plug this in here, okay, 1/2 V final squared minus V initial squared, and multiply it by m, now I am simply distributing this across what's in parentheses. And when I do that, I get 1/2 mass times velocity final squared minus 1/2 mass velocity initial squared. So I get all of that. And that, they say, is equal to work. Now, before I continue with the work energy theorem, I want to explain to you the definition of kinetic energy. So the kinetic energy, we use the symbol uppercase K uppercase E, of an object with mass m and speed v is given here. This is the energy that an object has when it is in motion. Object of mass m is in motion, it's moving. And this is called the kinetic energy of the object. So if you look at this 1/2 mv squared, you'll notice that I have that up here, 1/2 mv squared. Final minus 1/2 mv squared initial. So here what you can see then, this is clearly a change in the kinetic energy because 1/2 mv squared is kinetic energy. So I have final minus initial. So with that being said then, we have what we call the work energy theorem, where work is equal to the change in the kinetic energy. Kinetic energy final minus kinetic energy initial. That gives us 1/2 mv final squared minus 1/2 mv initial squared. So this is really, all of this, you want to just remember it. It just means the change in the kinetic energy. So the theorem says this: when a net external force does work on an object, the kinetic energy of the object changes by the amount of work done on it. So the work then is just an expression of the change in the kinetic energy when a net external force is doing the work. So that is considered the work energy theorem. So we have an example. So now we're going to solve this problem. So I'm going to go to the whiteboard and solve this problem. Give me a minute. Not in my textbook. Okay, so let's go to example 4 on our whiteboard. Okay, so let's go with this problem. Whiteboard. So it says the Space Probe Deep Space One was launched on October 24th, 1998, and used a type of engine called an ion propulsion drive. An ion propulsion drive generates only a weak force or thrust, but can do so for long periods of time using only small amounts of fuel. Suppose the probe, which has a mass of, so let's go ahead and identify what's given in the problem. So first we have our mass, 474 kilograms. It's traveling at an initial speed, so this is V initial, 275 meters per second. Let me turn my phone off. Give me a minute. Okay. No force acts on it except a, so the only force that's acting is only force that's acting is a 5.6 times 10 to the minus 2 newtons. So you can see this is a very, very small force, 10 to the minus 2. Okay. This external force, F, is directed parallel to the displacement. So parallel means that my theta is 0. You know, the cosine of 0 is 1. Okay. And, okay, the external force directed parallel has a displacement. So it moves a distance of 2.42 times 10 to the 9th meters. And the question is, determine the final speed. V final. Determine the final speed, assuming that the mass remains nearly constant, okay? So, we are applying a force. It goes through a distance, and we say when it goes through a distance, that's work. And now we just learned in the last frame that work is equal to the change in the kinetic energy. That's where you want to start. So we're doing this problem so I can explain to you how to get started. You know that you're doing work. And we just saw in the last frame that when we do work, that force causes a change in the kinetic energy. Now, how do we define kinetic energy? Remember, we said that the kinetic energy is defined as 1/2 mv squared. So when I say change in that, okay, that means I have the kinetic energy final minus the kinetic energy initial. And how we find kinetic energy? Final means the final what? Speed. The kinetic energy for the final speed minus the kinetic energy for the initial speed. So then I have kinetic energy 1/2 mv final squared minus 1/2 mv initial squared. That's all of that is just a change in the kinetic energy. Then how do we define work? Because it's parallel, theta is 0, then I just have what? Force times what? Distance. So look, force is given, distance is given, mass is given, the initial is given. So all I need to do is take this equation, and isolate the final. Okay? So the first thing I'm going to do is write the equation where this has moved to the other side. And of course, when we solve for the unknown, we write it on the left side. So I'm going to say 1/2 mass V final squared is Fs. This is negative. On the other side is going to be what? Positive. 1/2 mass V initial squared. Now, I want to get the final by itself. So what do? Multiply both terms by the coefficient of 1/2. The coefficient of 1/2, of course, is 2. So to get rid of this 2, to get rid of this 1/2, I multiply everything by 2. In other words, I multiply this side of the equation by 2 and this side by 2, which means I have to distribute 2 here and here. So I put a 2 here and a 2 here. Of course, that cancels that out. So this 2 times 1/2 cancel that out. So now I have mass V final squared is 2F times S plus mass V initial squared. Now I need to get rid of this M. So of course I'm going to do what? Divide the terms by M. And of course here the M's cancel out. The M's cancel out. So when I solve for this V final, I'm going to take 2 times F sub S divided by M and add to that V initial squared. So let's solve for V final square. So V final square is 2 times F is right here, 5.6 times 10 to the minus 2 newtons times S, and S is 2.42 times 10 to the 9th meters, and divide that through by M, and M is 474 kilograms. So let's do that part of the number first. So we have 2 times 5.6 times 2.42 divided by 474. Let's do that part first, and then we'll add the V initial square. Okay, let's do that part first. Let's see what we get. Someone please take your calculators out. Let's see if we can compare our answers, just in case we have an error. We can see what is correct.
Does that say 2 minus 12 times 10 to the 9th?
No, that's 2.42.
Okay.
We plugged in the S right there. Okay. So we have 2 times 5.6 times 2.42 divide 474. Okay. Okay. And when we get that answer, okay, in my calculator, I got 0.0571, and this is times 10 to the 7th. Okay, that's what I got. Now, what are my units? My unit should be meter square, second square. That's all I have left here. In order for these to add together, they have to be the same unit. So let's see very quickly what my units are before I go any further. So I have a Newton right here, and a Newton we know is a kilogram meter per second square. A Newton times another meter, so that'd be times a meter, and we divide it by a kilogram. Oops, divide it by kilogram. So that will cancel. So this unit here, this is meter square second square. Very good. The units have to match. Now I have V initial, which is here, 275, and I square that. So I have 275, and I square that. So now I have 75625. 75625. And of course, that is meters square, second square. Okay, now I need to add these two together. So let's just see if I can get this number written in expanded form, which means I got to go 1, 2, 3, 4, and then what? 5, 6, 7. I got to annex 3 zeros. 1, 2, 3, 4. See, 1, 2, 3, 4, 5, 6, 7. Is that correct? Yes. 1, 2, 3, 4, 5, 6, 7. Okay. Then we're going to add this number 7, 5, 6, 2, 5. And the units are meter square, second square. Okay, so now to find the final, I take the square root of that sum. So those numbers I add together. Okay, so I add to that 571,000. Okay, so under my radical, I have 6, 4, 6, 6, 2, 5 meter square, second square. Then I take the square root. Okay, someone has a question, let's see. Hold on. Okay, very good. All right. Keston has the answer. Okay, very good. So, Keston says answer is 804.1 meters per second. Okay, very good. Now, before I go back from this page, I'm sorry about this line going through here. I want you to see, because you have problems like this in your homework, I want you to see where to start the problem. So I'm going to go back now and show you where to start the problem. I know that sometimes I hear you say you don't know where to start. So let's go back to this problem right here. Let's see what's being said. Okay, let me go back one. Look what it says here. When a net external force does work on an object, so that when the force does work, that brings in the work equation, and the work equation is F cosine theta S. So when this work here, this force does work, the kinetic energy of the object changes. So what is the change? Okay, the kinetic energy changes, and we know that we always use this symbol delta to stand for change. So change in kinetic energy. So that is my work energy theorem. Just remember it like this. Work equals change in kinetic energy. Then we can expand work. We have an equation for that. That equation is F cosine theta S. And this means change, which means the kinetic energy final minus kinetic energy initial. And how we find kinetic energy? 1/2 mv final squared minus 1/2 mv initial squared. So that's what you want to, that's how you want to think about this problem. You want to think about it first, whenever the force is doing work, and work means that it's moving at some distance. If it's moving at some distance, it's doing work, and that is the change in the kinetic energy. Okay. So here we have the problem that we just solved. Now you notice here that all of this is what we just did. We simply isolated the equation first. I suggest that you always isolate the symbol, the term, the variable that you're looking for before you plug in all these numbers. I would suggest that you do what we just did. Get the equation for V final square first, and then you can solve it more easily, rather than having to carry all these numbers as you're trying to get this V final square by itself. Now, apparently he must have averaged some numbers up before he finished. So he got 805, but we got close enough. I think our answer is probably more accurate. Okay, very good. I want to go now to the gravitational potential energy. So for gravitational potential energy, this is moving an object against the force of gravity. You know that the gravity wants to pull it down. Anything that's released will fall straight down. So it means when we push, when we're working on it, we're lifting it up. We're doing work against gravity. Now, this author's notation is a little different from what I have normally seen. So I just like to say that work against gravity is just mgh, where h will represent the distance that it actually moves, the actual distance that it moves from its initial position to its final position. And that's a lot easier to remember. Work against gravity is mgh. Now you notice that mg, we've already defined that as the weight. So what you're actually doing is just lifting a weight through some height, and that's considered work against gravity. Now, this picture is simply saying that the work against gravity is not dependent on the path taken. In other words, if I lift this basketball to a height or drop it to a height, it doesn't matter if I go up and around or however I move it, the distance that I have moved is the height, the absolute distance that I have moved. So you see, even though I went up here first and came back here, this is my S, this is my height. Okay, so here we have another example. What is the gravitational potential energy? Now, the gravitational potential energy is going to be the same as the work done against gravity. So let me go back and explain it to you again. When I do work, I move this weight to a certain height. And once the object is sitting at a certain height, that's considered stored energy. So I've done work against gravity, and now that stored energy, due to it being elevated to a certain height, is actually the potential energy. Well, the potential energy is just the weight at that height. So I'm giving it to you in a more simple form so you can understand it a little better. So let me go now to our equation quiz here. Okay. So we had work horizontal. We said that work horizontal was F cosine theta times the distance. And of course, the unit is joule. We did work against gravity. So that work we said is mgh, and that's also in joules. We said kinetic energy, we said is 1/2 mv squared. And what do you think the unit is here for kinetic energy? Well, actually the unit is also the joule. So let me go up here and show you where I had here, okay? Let's go up here and look at this. You see a kilogram meter per second square, because this is 1/2 mv velocity squared. In other words, we said that kinetic energy is 1/2 mass, that's in kilograms. The speed is in meters per second, but it has to be squared. So of course we have a kilogram meter square per second square. If I break that down, I can write that like this: kilogram meter per second square times a meter. If I group it like that, I can easily see that this is a Newton meter, which is a joule. So a kilogram meter square per second square is also a joule, which is my unit of energy. So therefore, the unit of work and the unit of energy is the joule. Okay. Then we said that potential energy is just the energy stored by an object that has weight, which is mg, at a certain height. So potential energy is also in joules. Okay. Now, oh, I had this on the wrong. Let me say I had this on the wrong one. Hold on. Let me put this. Okay, trying to line this up better. Hold on. I want this to be right. So once I leave it, I can't get it lined back up. I'm trying to line it up. Okay. All right. That's best I can get right now. Okay. I want to put in the work energy theorem. So we said that this is also in joules. And we said the work energy theorem is work is equal to change in the kinetic energy. And then we expanded that earlier. Then we said the potential energy is mgh, and that's also joules. So I want to do a couple of more equations before we do a few problems. The other equation we want to do is total mechanical energy, power, and power. Okay, let me go to Her notes. Okay. Okay. Okay, we've already defined gravitational potential energy. We've defined that already. Okay. Now, I want to go to, there's so much to cover. I want to go to the work energy theorem. So, first of all, what is the conservative versus non-conservative forces? A conservative force is one where it doesn't matter the path that I take, I will end up with the same amount of work done. So we have conservative forces and non-conservative forces. But we're going to just stick with the what is meant by the work energy theorem expanded. So if it is a non-conservative force, the work done is not only equal to the change in the kinetic energy, it's also equal to the change in the potential energy. Now, if the net work on the object by non-conservative forces is zero, then its energy does not change. So these are non-conservative forces, and my equation is that all the energy final is equal to all the energy initial. And this is the conservation of mechanical energy. The way that you have heard that equation, I mean, that statement before, is that work is neither created nor destroyed. It is just, I mean, energy is neither created nor destroyed. It's just changes its form. So this is a form of the conservation of mechanical energy. Now, what do I mean by mechanical energy? When I say mechanical energy, I'm eliminating chemical energy and energy like that. So in this course, when I say mechanical energy, I'm referring specifically to the kinetic energy and the potential energy. So the total mechanical energy, E, equals the kinetic energy plus the potential energy of an object remains constant as the object moves, provided that the net work done by external non-conservative forces is zero. So this is what I want to show you in this picture. The conservation of mechanical energy. What we have here at the very top, we have this car at the very top. And the initial speed is zero. The initial speed is zero, meaning what? There is no kinetic energy. So the kinetic energy is zero. All the energy that it has is because of its height. So that's potential energy. So the total energy is the kinetic energy plus the potential energy. Then these dots represent the car at different heights. So now the car has begun to move. And we know that once it starts to move, it has some speed now. It's no longer zero. So that means it has some kinetic energy. And at this point, the kinetic energy is 200. But because of the conservation of mechanical energy, the energy that it has gained in kinetic energy was a reduction in potential energy. And of course, it has less potential energy, as would be expected, because it has less height. Because before mgh was, h was here. Now h has been reduced. If h is reduced, then of course my potential energy has reduced. Then the object goes a little further down, and not only has it increased in its kinetic energy, we know from the earlier chapters that it has also increased in speed because it's coming down under the influence of gravity. The car is now moving faster. And as it moves faster, of course, it's going to increase its kinetic energy. As it goes down lower, it's going to decrease its potential energy. But in every instance, the total energy is conserved. Conserved means it doesn't change. Then finally, it reaches the bottom. So now it's going to speed out with some great speed compared to what it had initially, which was 0. And it's now at the bottom here where my H is 0. And if H is 0, then of course the potential energy is now 0. So all of my potential energy has been converted into kinetic energy. So that's why we said that the energy is neither created nor destroyed, it is transferred. So this is just a simple picture to show you the transfer of energy. Okay. Now, with that being said, we can actually solve some of these problems that we solved earlier using our kinematic equations. Now we have an even easier way to solve these problems. And the reason is because now we're introducing the conservation of mechanical energy. So this example says, a motorist is trying to leap across the canyon by driving horizontally off a cliff at 38 meters per second. Ignoring air resistance, find the speed with which the cycle strikes the ground on the other side. Now, if you notice in your midterm exam, we had to solve for the final speed. There was an object, I can't remember now if it was an object thrown at thrown horizontally, but in this case, all we know is that he has initial speed 38 meters per second horizontally, okay, which means it's in the what? In the X. Then we have the height, and then it says right here, ignoring air resistance, find the speed with which the cycle strikes the ground on the other side. So if you remember back before when we did this problem, this is a parabola, half of a parabola, and we had to solve this problem with many steps. But we're going to see here now how to solve it more easily. So we know that the energy final must equal to the energy initial. So energy final is both what? Potential, MGH final, and kinetic. Also, the energy initial is what? Potential plus kinetic. Now, once I write this equation, you see I have M, the mass, in every term. So therefore, the mass can cancel. And that's why they didn't give you the mass, because it wasn't even needed. Now, I want to find the final speed when it strikes the ground, which is V sub F. So I need to rearrange this equation to solve for V sub F. When I do that, I get this equation. Because V sub F is squared, I need to take the square root. So now I'm able to solve this problem in basically using one equation. Whereas before, when we solved the equation, and you can look in your midterm, you will see we had to first find the time, and then we had to find the distance, or we had to find several things. But now we see there's a much easier way to solve it using the conservation of mechanical energy. Okay, so those are the main items that I want to cover in this chapter. about the energy. I have two more frames, two more equations real quickly. Okay, the definition of average power. So this little bar just simply means average power. You won't have to use it every time, but just know that we're referring to the average power. And the average power is the work done per unit time. So work is measured in joules, time is measured in seconds, and a joule per second, we call that a watt. And the watt is the SI unit for power. So this is the equation for power. Okay, equation for power. So then we can also write power as a product of force and speed. So you can probably see that right here. Okay, we said work was force times distance over time. And if we rewrite this distance over time, we call that what? We call that speed. So distance over time is speed. So we can also have this as an equation for power. So here we have power is also force times average speed. Okay. Let me show you. Oh, that's all I have there. Okay. I have some problems. Let me go now and show you the rest of the equation quiz. Okay. So here we have the rest of our quiz, and we said that the total mechanical energy, we use the symbol E, is the kinetic energy plus the potential energy. And of course, that's in joules. Then we did power. And power, we said, is work per unit time, and that's in watts. So you notice now that we have uppercase W for the unit of work. In the equation we use for work, we use uppercase W, and for power, the unit, we use uppercase W. So of course you know that in the equation, the uppercase W stands for work. As a unit, the uppercase W denotes watt. Okay. Now, because we know that work and energy are the same unit, power is also energy per unit time, which is a joule per second. And that gives us a watt. And then we saw that power is force times speed, and that's also a watt. So those are the equations from this chapter. The other item I want to show you is here. What is a joule per second? We say that is the watt. Okay. Oops. That's a watt. And then up here, I wanted to bring your attention to a conversion that I have up here. Okay. So the watt is the SI unit for power, but for us, we are accustomed to the horsepower. So the SI unit for power is the watt, and we have a conversion. And the conversion says 1 horsepower is 700, we'll just round up to 746 watts. That's a conversion you want to use because this is an English unit, this is the SI unit. So with that being said, we can look quickly at our homework. We don't have much time, but we'll look at it kind of quickly. Okay. All right, so here we have the homework. And I want you to go through and solve these problems. This is the homework. I've sent it to you. And we'll discuss these tomorrow. Just keep in mind, I thought I had one on here where you had to do, oh, I don't even have all the homework on here. Number 9, okay. Well, in your notes, I'm going to send you the other problems because you have some where you have to use the work energy theorem, and also you have to use the equations for power. So that got left off, but I'll send that to you. Okay, so the main thing now, class, will be for you to have your lecture notes, hopefully your textbook, because I had to skip through this kind of quickly, and your equation quiz, so that you can have all of your equations in front of you when you start to do the homework. So I will send you a few more problems, and this will not be due until Monday. So I hope you have a nice weekend. Look for this homework, the rest of the homework. Go ahead and get started on the first 9 problems, and I will send the other problems over the weekend, probably tomorrow. Okay, do we have any questions now before we end our lesson for today?
You said you sent this equation quiz with the notes because I didn't get it. If you did.
Okay, look again because it came a little later. First, I sent the lecture notes, and then right before class, I sent the equation quiz and the first part of the homework. Oh yeah, this is homework 6.1. So 6.2 I haven't sent yet. Yeah, that's what it is. So do you see it in look in your email? You still don't see it?
Yes, ma'am. I only have the PowerPoint and the first homework. That's it for chapter 6. That's all they came.
The equation quiz wasn't there?
No, ma'am.
Okay, all right. So I'll send the equation quiz when I send the second part of the homework, or I can just send the equation quiz right away, and then I'll send the second part of the homework later. Okay, thank you for letting me know that.
You're welcome.
Okay, anything else? Okay, so you can sign your name as you are leaving, and I will, so next week we'll start the week off by solving problems from chapter 6, and then we'll just keep moving right along. Okay, have a blessed weekend.